We're back. So once again, we have Umesh, who's going to be talking about microservices architectures for CubeSat mission control systems.
Hello, I'm Umesh. We're part of ESTCube. We launched the first Estonian satellite in 2013. We're planning the next by 2019. And my role is in mission control system. And the mission control system is typically between the ground station, the operator, and the satellite. And you can begin as a telecommunication company where we transfer data to the crowd. We also participate in smart control. There are many subsystems that the satellite has on board, and we are part of the ground support system. And our role is basically to be an extension of the ground system to track and maintain communication with the spacecraft and to control and exchange any data and analyze the authorized person. And the team is made of 10 plus passionate students. We've been working on this for like 10 plus months. And what we're trying to do is to follow industry standards and to even lead in some of the concepts regarding the third mission control systems. So, on that point, I'm going to show you one of these. So this is, no offense, but this is what we think the current mission control systems, because CubeSat missions look like. They're big, they're outdated, and they don't talk to each other. So, we want to introduce the concept of collaborating for bigger missions and bigger organizations like NASA and ESA. They have collaborations for mission data and everything. But for smaller CubeSat missions, they're usually independent and there's no sharing of information or there's no sharing of resources, which is also important. So our vision is to have something which is fault tolerant, scalable, and secure, and something which is upgradable and mission migration friendly, which means you invest in one type of vendor, one type of technology, you should be able to leave as soon as possible. When something new pops up, you don't get stuck in, which is what usually happens. That's why people are reluctant to change from one technology to the other. We want to alleviate that. And this is also very important. This, like, it should be easy for newcomers to adopt any new technology that comes out. So that's one of the concerns we're trying to address. And to build an MCS, there are a couple of challenges. The first is coordination. There's multiple spacecraft. We have a set of time. We have to schedule commands. We have to ensure reliability. And it's also heterogeneous because if you have multiple sets of hardware, it has to work in perfect sync. We also try to inculcate automation to ensure, like, the operator doesn't sit there at 2 a.m. trying to control the satellite. But we divide the tasks into periodic tasks and manual override tasks and normal tasks, so automation can be achieved to a better degree. And deduplication as well. So this is the architecture and planning. So this is called microservices architecture. And we have like 50 plus, instead of having one big piece of software that's called the MCS, we have like 50 different small applications, and it's growing, that combine to make the ESTCube mission control system. It's powered by a technology called Docker. So a container or a service is basically one small application in a box, and it does one job and it does it properly. So it's similar to a drill. It does one job. You can use a drill to do anything else, but it's usually a specialized tool. So that's what we plan. So we have a tool for every purpose. One for weather, one for the graphical user interface, one to fetch the TLEs, one to process the data, one to split the packets, one to join the packets. So you get the idea. So everything has to have like a different application. There's no multitasking for applications. Every application does just one thing and does it perfectly. And you might think like containers are similar to virtual machines, which they are, but they are like much better in the fact that virtual machines usually have their own entire operating system. Meanwhile, containers just have the necessary libraries, and they're much more resource efficient, and you can put in more of independent applications on the same machine or hosts. And regarding health, if you have like multiple containers, some of them are going to go down, go up, but with the microservice architecture we have, it's all fault tolerant and it can take care of itself. And regarding scaling, sometimes you need more resources, sometimes you need less. So this is a concept that we're bringing in from the cloud, and you hear this most of the time. So you can scale up as much as you want. After you're done, you can scale down, and you can live with the resources that you just need. So on-demand usage of resources. And you can also have something like multiple versions of the same piece of software running at the same time. This is to take care of compatibilities. Some applications will only support version 1, but because of that, you can't use the other. So we can have multiple versions of the same thing, so it supports more applications. And then scalability across hosts. Scale across hosts horizontally, and we're trying to use Kubernetes. And this also ensures in self-healing systems, one host goes down, another host takes over. So, and of course there are some cons as well. The pros are you can build once and run anywhere. So if we build a module for ESTCube, you can just take it away and put it in your system. It's going to work because it's independent. It's not dependent on anything. So that's the policy where you build once, run anywhere. That's literally anywhere. And resource utilization is also a very good proponent for this. And the concerns are, if you don't do it properly, it's going to get more complicated. It's just like making an omelette. You start making it, if you don't make it properly, you're going to end up with scrambled eggs. So here it's something similar. If you can't orchestrate the containers properly, it's going to grow into a big mess. Security concerns are being addressed more and more, so again, still something to look into. We also have something like a hardware test platform. So there's a copy of the satellite on ground, and before sending the command or the chain of commands up there, it's automatically tested down here, and then validated and only then authorized to go up there. So we use something called TTCN, which is quite popular in the telecom industry, and we're using a solution by Elvier to test every command on board on ground first. So then we also use something called model-based testing for more reliability. This is to test behavior which can't be tested by software itself, or like just by the test platform itself. So imagine we want to we have scheduled the command to take a picture after 2 months, but after a week we turn off the camera. So the command that has to run after 2 months won't work. So this model will tell us those kind of unexpected behavior and warn us of potential scenarios that conflict each other. The inspiration for this also came from the Radio Aurora Explorer CubeSat missions. And then we also have a scripting engine, which we believe would speed up mission control system operations. Rather than typing and clicking, we support scripting capabilities, and scripts are always quicker than tapping or clicking. And then this is something that we try to close. We are trying to connect to different ground stations across the world, and every ground station would have a beacon, like a calendar, where we could schedule resources. And it's easier for people to test out ground stations. They don't have to sign an entire agreement and then use their resources. They can use it for like 10 minutes to test it out. You want to test out something in South America? Yes, you can just do it for 10 minutes. Because it's all on a slot basis. That is something we have come up with. And then, because there are so many containers, we need something to orchestrate them. So we have something akin to a knowledge base that consolidates this information and spews out. And if you want, we also have something like contact automation. So this is intelligent enough to look at the overpass and then reschedule the packets if transmission failure occurs. Under ground station 1, if you couldn't transmit the 10 packets that you needed, it's going to automatically schedule it for ground station number 3, which is like on the same overpass. So that's something that we're trying to make more and more efficient. contact information. And we also have something called a data processing platform, which is solving the problem that most of the data analysis and processing is done independently. Like people take it on their own server networks or their own machines and then they come up with results. But what if you could test or you could see the experiments that are done by a colleague? And this is an entirely online system, so there's no installations involved. You can add libraries as you wish. So there might be, these are the current libraries that we support, but you can easily add as many libraries as you want. And this shows just like out of this many services, you just need to customize a couple to use it for your own mission. So that's one of the advantages of having Microservices architecture. What we're looking for is we're planning to offer the MCS as a service, and we're also looking into potential partnerships with ground stations or other missions for tracking their satellites or resource sharing. So if you're interested, we can talk afterwards. The takeaway is make everything modular, divide the whole thing, don't put all your eggs in one basket, think of scalability and think of interoperability. So yeah, thank you.
Okay, we're happy to take questions, if any.
Hi, it's really interesting that. But I was wondering if you could elaborate on the concerns over security. As someone who's not familiar with that aspect of the software and the modularity, why is security a concern?
Okay, so you're trusting your satellite mission on a technology that someone else has built. So you don't know really what's going on, and that's one of the concerns. The second concern is, even if you're using something open source, you're not going to compile it from scratch. You're probably going to use a binary that's been compiled and you trust it. So there are all risks that are associated with an open source project, and because this is a relatively new technology, Docker was introduced in 2013. So there might be loopholes that we should be possibly looking into. So it's good to have someone, some security expert look over your implementation.
Finally, somebody's doing this.
Oh, yeah.
I'm just curious about the integration of your system with the infrastructure of the ground station. Do you plan some standardized interface?
We are building the next set of interface. That's what we call the beacon. Yeah. So we're going to have a smaller version of the container running on the ground station. So it's going to be open source. So a ground station can potentially use this to sell their service as well, like this time slots. And for us, the benefit is we can see when they have the time slot.
So you end up on some top-level data handling.
Yes.
You are really not controlling the ground station.
No, we're not, and they won't let us. So because there's a lot of red tape around controlling ground. All we do is it's a simple calendar where you can book meetings and slots. So something similar for satellite broadcast.
The reason why I'm asking is that there are many stations which are really completely online. They have no operators there, fully automated. So it would be also cool if this gets some sort of standardized to some certain stage, so people don't have to be bothered with developing this again and again.
Yes, you're right. So that's thank you. That's the concern that we're trying to address here. We're trying to lead and build the next standard for ground stations.
Any further questions? No? In that case, let's thank our speaker once more.